LangGraph state persistence mechanism relies on the checkpointer interface, specifically implemented here through SqliteSaver, to manage checkpoint storage and retrieval in a structured format. This artifact demonstrates how checkpoint data, including channel values and versions, is serialized and persisted using a SqLite backend, with configuration handling for thread-specific operations. We're about to examine the initialization of a SqliteSaver instance, the construction of a checkpoint dictionary containing version channel data, and the subsequent storage and retrieval operations. The code will reveal how configuration objects control checkpoint namespace isolation while maintaining consistency across read and write operations.
From LangGraph, checkpoint, SqLite import SqliteSaver. Write config equals configurable. Threaded, 1 checkpoint ns. Read config equals configurable. Threaded, 1. With SqliteSaver from con string as checkpointer. Checkpoint, v4. TS 2024-07-31T 2019 804,150 plus 00 00 id 1F4F797-8335-6301-8A1503 F9B875. Channel values. Mikey, meow. Node. Channel versions. Start 2. Mikey 3. Start node 3. Node 3. Version scene. Input. Start 1. Node. Start node 2. Hash store checkpoint. Checkpointer, hotwrite config checkpoint. Hash load checkpoint. Checkpointer, getRed config. Hash list checkpoints. List checkpointer, listRed config.
This code demonstrates checkpoint persistence using LangGraph's SqliteSaver, a pattern for maintaining state across workflow executions. The example shows 3 core operations: storing a checkpoint with put, retrieving it with get, and listing available checkpoints with list. The checkpoint itself contains version channel data, including values like myKey, meow, and metadata tracking which nodes have processed which versions, enabling precise state recovery. The SqliteSaver acts as a lightweight persistence layer, using SqLite for durability without external dependencies. The write config and read config dictionaries specify the workflow context via threaded, allowing isolation between different execution threads. This approach trades off some scalability for simplicity, making it ideal for single machine workflows or testing scenarios where you need reproducible state management. The version tracking in channel versions and version scene enables LangGraph's incremental processing model, where nodes only process new updates. This pattern is particularly useful when testing stateful agents, as mentioned in the context, since you can recreate the graph with a fresh checkpointer instance while preserving the exact execution state. The SqLite backend keeps the implementation portable, though for production systems with high throughput, you might consider alternatives with better concurrency support. Let's break it down.
From LangGraph, checkpoint, SqLite import SqliteSaver.
Imports the SqliteSaver class from the LangGraph. Checkpoint, SqLite module, which provides functionality to persist checkpoints in a SqLite database.
Write config equals configurable. Threaded, 1 checkpoint ns.
Creates a dictionary named writeConfig with a nested structure containing a configurable key. This nested dictionary holds 2 string values: threaded, set to 1, and checkpoint ns, set to an empty string. The structure suggests configuration for thread identification and checkpoint namespace in a LangGraph workflow, though the specific usage isn't visible in this line.
Read config equals configurable. Threaded 1.
Creates a dictionary named readConfig with a nested structure containing a configurable key that maps to another dictionary with threaded set to the string value 1. This appears to be configuring a thread identifier for some configurable component in the system.
With SqliteSaver from constring as checkpointer.
Creates a context manager using SqliteSaver from constring to initialize a checkpoint saver with an empty connection string, binding it to the variable checkpointer. This establishes a temporary SqLite-based checkpoint storage mechanism that will be automatically managed within the with block, ensuring proper resource cleanup upon exit.
Checkpoint equals.
Initializes a dictionary variable named checkpoint with an empty dictionary value. This creates a mutable container that can store key-value pairs, typically used for maintaining state or configuration data in LangGraph workflows. The empty initialization suggests it will be populated later with checkpoint data, such as state snapshots or intermediate results that need persistence across graph executions.
v4.
Sets the version number to 4 in what appears to be a configuration or metadata object. The key v is assigned the integer value 4, likely indicating a protocol or schema version for compatibility purposes.
TS 2024-07-31T 2019 804,150 plus 0000.
Assigns a timestamp string in ISO 8601 format with microsecond precision to the key TS, representing July 31, 2024 at 20:19, 804,150 UTC.
id 1F4F795-8428-6428-8001 -8A1503 F9B875.
Assigns a unique identifier string, 1F4F797-8428-6001-8A1503 F9B875, to the key id in what appears to be a dictionary or JSON structure. This UUID serves as a persistent identifier for tracking or referencing this specific entity across operations.
MyKey meow.
Assigns the string value meow to the key myKey in a dictionary, establishing a state variable that can be updated by nodes in a LangGraph workflow.
Start 2.
Sets the starting node for the graph execution to node 2, where start is a special key in LangGraph that specifies the entry point, and the value 2 indicates the second node in the graph's node list.
MyKey 3.
Assigns the integer value 3 to the key myKey in what appears to be a dictionary or state object. This represents a state value that can be updated and tracked across graph nodes in LangGraph workflows.
Start node 3.
Sets the starting node for the graph to node with identifier 3. This configuration specifies that execution should begin at the node labeled 3 when the graph is run.
Node 3.
Assigns the integer value 3 to a variable or field named node. This establishes a numeric identifier or reference point within the graph structure, likely representing a specific node in the workflow. The exact purpose depends on the surrounding context, but it creates a direct association between the label node and the value 3.
Input
defines an empty input dictionary for a LangGraph node or workflow. This establishes the initial state structure where no input data is provided at the start, allowing the graph to begin processing with a clean slate. The empty dictionary serves as the foundation for state management, which subsequent nodes can populate with the key myKey as they execute.
Start.
Defines the entry point node named Start in a LangGraph workflow configuration. This node serves as the initial execution point when the graph begins processing, with its behavior and connections to other nodes specified within the associated object. The exact functionality depends on the properties defined within this node's configuration block, which isn't visible in this segment.
Start 1.
Sets the initial value of the state key, myKey, to 1 when the graph starts execution. This establishes the starting point for stateful operations in the workflow.
Start node 2.
Sets the starting node for the graph to node with identifier 2. This configuration specifies that execution should begin at the node labeled 2 when the graph is run.
Checkpointer putWrite config checkpoint.
Calls the put method on a checkpointer instance to store a checkpoint. Passes a write configuration object, the checkpoint data to store, and 2 empty dictionaries as the last 2 arguments. The immediate effect is persisting the checkpoint state according to the provided configuration.
Checkpointer getReadConfig.
Calls the get method on the checkpointer object, passing readConfig as the argument. This retrieves a checkpoint based on the configuration provided in readConfig.
Hash list checkpoints. List checkpointer listReadConfig.
Calls the list method on the checkpointer object, passing readConfig as an argument, then converts the return checkpoints into a list. This retrieves and displays all available checkpoints filtered by the provided configuration. The SqliteSaver implementation demonstrates LangGraph's checkpoint persistence pattern using Sqlite as a lightweight backend. The workflow begins by configuring thread isolation through writeConfig and readConfig, ensuring checkpoints are properly namespaced. The checkpoint itself encapsulates both state values like myKey, meow, and version tracking metadata that enables incremental processing. When the checkpointer stores this data via put, it persists the entire execution context, including which nodes have processed which versions. The subsequent get and list operations then retrieve this state, allowing workflows to resume from exact execution points. This approach trades some scalability for simplicity, making it ideal for testing scenarios where reproducible state management is critical. The versioned channel data and thread-specific configuration work together to create a portable persistence mechanism that maintains consistency across graph executions.
The empty threaded whispers to the checkpoint, yet meow echoes back from channel values.